Today's problem is cycle and directed graph. This is on InterviewBit, and so you can pause the video at this point, go over to InterviewBit, solve this problem, and then come back and we can review the implementation. This is rated as easy. I don't know if I would rate this as easy. I mean, it's easy for some subset of software engineers who've been through a CS degree and taken algorithms classes and data structures and software engineering and things like that. But there's a 48% success rate. It's fairly high. So anyway, I mean, once you understand the pattern, it is a pretty easy problem. So let's see. Asked at Amazon. Problem description: given a directed graph having A nodes. That's one of the inputs. A. So we have A nodes, A vertices, and we also have a matrix B of size m by 2. This represents the m edges such that there is a directed edge from node B at I0 to node B at I1. Find whether the graph contains a cycle or not. Return 1 if there is a cycle, otherwise return 0. And some notes. The cycle must contain at least 2 nodes. There are no self loops in the graph. Okay, yeah, those two kind of go together. There are no multiple edges between 2 nodes. The graph may or may not be connected. Nodes are numbered from 1 to A. That's good to know. It's not the customary way of doing it. Usually we start the numbering at 0 because it syncs up better with 0 indexed programming languages, but okay. The nodes are numbered from 1 to A. If you're using global variables, make sure to clear them. We're not going to use any global variables. A, number of vertices in the graph will be between 2 and 10 to the 5th, 100,000. The number of edges will be between 1 and the minimum of 200,000 and A at A minus 1. Now, if I understand the numbering right, A at A minus 1 would just be A minus 1. If you have some number of edges that's greater than or equal to the number of vertices, then you have to have a cycle. You've got too many edges, which is why that 200,000 is too high. If you can only have 100,000 nodes, you can't, well, I mean, I guess you could have 200,000 edges, but yeah, there's definitely going to be a cycle there. Okay. And the edges in the edges list will be valid. They'll be between 1 and A. First argument is that, okay, so we already went over that. Return 1, we already went over that. Input, is there a cycle in this first one? Let's see. All right, well, we've got an edge that goes from 1 to 3. We've got an edge that goes from 3 to 4. We've got an edge that goes from 4 to 1. Now we're back where we started. So that's a cycle. How about this one? 1 to 2, 2 to 3, 3 to 4, 4 to 5. No cycle there. So 1 has a cycle. 2 doesn't have a cycle. All right, let's take a look at how we might implement this. Let's see. All right. Directed graph. Now, I created an object here called digraph. It's a directed graph. You don't have to do that. If you're interviewing for a position involving object-oriented programming, it's better, I think, if you do implement a graph object, because it's a chance to demonstrate your ability to create and use objects, custom objects. But you don't have to. What you do have to do is you have to get this input here into what are called adjacency lists, which is one of the principal ways of representing graphs. If you just take this, which is just a list of edges, and you want to find out what are the edges that are coming out from any particular vertex. Well, in this format, the only way you'd be able to find that is you got to go through the whole list every time. That's not what you want. What you want is adjacency lists. How do we implement adjacency lists? All right, well, we should probably look at that. So, digraph. We're going to create a directed graph. What you usually pass into the constructor of a directed graph is the number of nodes. In this case, that's not what we want to do. If you start the node numbering at 0, you pass in the number of nodes. Now, directed graph. All right, let's take a look at that. We're going to pass in a plus 1. Here is our adjacency. Here are our adjacency lists. You can do this as either a list of lists or as an array of lists. The index or the number of any particular node corresponds to an adjacency list in the list of adjacency lists. I didn't say that very well. Let's keep going, see if I can do better. Directed graph. So what comes in here is, again, typically number of nodes. In this case, it's a little bit different, because if we have A nodes, then those nodes are going to be numbered from 1 to A. And we want our indices to correspond to the numbers of the nodes. Now, we can't get indices from 1 to A with an array of length A. We can get indices of 1 to A in an array of length A plus 1, so that's what we're going to do. All right, so we send in A plus 1 and we create an adjacency list, which is an array of lists. Yeah, I actually feel like I'm doing such such a bad job of explaining adjacency lists. Let's just go ahead and draw. Let's just go ahead and create some adjacency lists here. Let's do it for example 1. So we'll create the directed graph. How many vertices do we have here? We have 5. So we would create an array of length 6. We have 0, but we're not going to use it. These are the indices. 0, 1, 2, 3, 4, 5, 6. Right? And then we'll have lists. We'll start here. 1. All right, 1 has an edge to 2. 4 has an edge to 1. 2 has an edge to 4. 3 also has an edge to 4. 5 has a length to 2. You know what? I don't know why I put that 6 there. And 1 also has a length, an edge to 3. So that's what adjacency lists would look like. So now, from any node, we can look it up in the array and say what edges are coming from this node. All right, so that's what we want our adjacency lists to look like. Let's see, create the digraph for, oh, okay, wait, one more thing here. Create the digraph, and initially we put an empty list in each element of that array, empty list. All right, next, for each edge in B, we get the start vertex, the end vertex, and we add an edge. Again, you don't have to do this within a graph object, but add edge means in the adjacency list for vertex V, add W to that list. Okay? Now what? States. Okay. A node can be in one of three states. One is we haven't visited it yet. Two is we are currently visiting it. We're going to do depth first searches here. So if a node is visited during a depth first search, it is marked as visiting. Okay, that way we know if we hit it again that we've got a cycle. All right, 2 means this node has been determined as a safe node. All right, again we need an array of size A plus 1 so that we can use vertices as indexes. Let's initialize cycle to false, and then for each vertex from 1 to A, we do a depth first search. We're going to pass in the vertex, the graph, and the states. All right, so the vertex comes in. Now, if this is a recursive search, you can see here that we're calling it recursively. If we're currently visiting a node, then we got a cycle, so we return false. If we have already determined that a node is safe, then we'll return true. Otherwise, we'll mark it as visiting. And then for any nodes that have a directed edge from this node, we will do a depth first search. At any point, if this depth first search leads to a cycle, then we return false. If we're able to get through all of the adjacent nodes without visiting a node twice, that is a safe node. It just all paths from that node lead to terminal nodes, meaning nodes that do not have any outgoing edges, or other safe nodes. So we mark it as safe and we return true. Okay, so that's what we have here. Create the adjacency lists representing the graph, and then for each vertex do a depth first search. If keep track of the states of the nodes. If you get a cycle, then we set cycle to true and break. We're done. We're going to return cycle true. If we get through all the vertices, we didn't find a cycle, then cycle is still set to false and we return false. All right, let's run this. All right, thanks for watching. If you found this helpful in your understanding of graphs, depth first search, hit like, subscribe, check out the playlist on your screen. There's more videos to level up your interview skills. The video description and the pinned comment have links to a free coding interview patterns PDF. If you're interviewing, you need that. It includes depth first search, so you can download that immediately, totally free, and we'll see you next time.